Fire the X-ray laser!
To most of us, an X-ray laser sounds like a gimmick from a 1960s space drama. But the X-ray lasers at the University of Colorado Boulder's imaging lab are very much down to earth, putting some of the smallest things in the universe on the big screen. That's right, these lasers take pictures. Images of molecule-scale events so infinitesimally small and fast that previously, capturing them was only possible in enormous miles-long research facilities. But now, thanks to Kapteyn and Margaret Murnane, we can record nature's smallest things in action with a device that fits on your kitchen table.
We met in a lasers physics class, embarrassingly enough.
Kapteyn and Margaret Murnane are married to their work.
He doesn't want me to tell the story.
No, she embellishes it a little bit more than I would.
And to each other.
He, at the time, had long, blonde, curly hair and bright yellow pants and a pink t-shirt, and I had never seen a physicist like him.
After the pair graduated from UC Berkeley, Murnane, raised in rural Ireland, and Kapteyn, who grew up in urban Chicago, decided they were a package deal, only accepting professorships at universities willing to hire both of them. Kapteyn and Murnane began a lifelong collaboration, pursuing a passion that very few married couples share: X-ray lasers. Just as X-ray light is great for imaging bones, in laser form, it's also perfect for imaging molecules. It works a little like the flash on your camera. An X-ray laser beam flashes on, say, a segment of DNA, then the light strikes an imaging sensor. But the holy grail for scientists is the ability to see small-scale events unfold in motion, like electrons moving in a material or chemical bonds forming in DNA. A window into the moving molecular world has vast implications in medicine, computing, manufacturing, and most importantly, deepening our understanding of nature. But filming at the nanoscale is challenging. Some events occur in as little as 1 quadrillionth of a second. To record these images, an X-ray laser beam has to pulse fast, really fast.
This camera is a loose analogy. When it opens its shutter, light enters and hits the sensor. If we leave the shutter open and film something really fast, like an exploding firecracker, we get an image like this. Long exposures of things that move fast produce blurry images. The solution is to open and close the shutter quickly, letting only short bursts of light hit the sensor at once. If we do this a few hundred or thousands of times a second, we get crisp, moving images.
Imaging motion with X-ray lasers follows a similar principle. Instead of a shutter opening and closing, the X-ray laser pulses, sending out short bursts of light over short periods of time. The faster the event, the faster the laser needs to pulse, and events unfolding at the nanoscale are some of the fastest in the universe. Filming them can require laser pulses 1 trillion times faster than the flash on your camera. Now, in the 1980s, making X-ray lasers like this was a challenge. The only ones in existence were massive billion-dollar apparatuses, miles in size, too big to be practical. Kapteyn and Murnane wanted to shrink them, making them small enough to fit in a lab and affordable enough for universities to acquire them.
It's something that literally was thought to be impossible.
It took decades of research, but in the end, the husband and wife team prevailed, capitalizing on a series of breakthrough discoveries in quantum physics that allowed them to design ultra-fast X-ray lasers small enough to fit on your dinner table. They even improved the speed of the pulses in the process. Their lasers can achieve pulses so fast they're measured in attoseconds. How fast is that? Well, a single attosecond is to a regular second what 1 second is to roughly 14 billion years.
We can see the fastest motions, the fastest energy being captured.
Kapteyn and Murnane's X-ray lasers are paving the way for chemists to make better fuels by watching chemical reactions, for neuroscientists to design better drugs by watching the molecular brain at work, for manufacturers to design smaller, faster processors and stronger, lighter construction materials by seeing how electrons move within the materials, and for bettering our understanding of physics itself.
What motivates me is this concept that light is energy in its purest form, and everything we do requires energy. So if we can control light, we're controlling our destiny in some sense. We keep plugging away at it, and it keeps
Surprising us.
Keeps surprising us. Yeah.